sounds like it should be something from the Schubert calculus. There should be some kind of reciprocity theorem, changing q to minus q, that would tell you a priori these cells are eliminated and those cells get punctured in this way. Right now I don't know how to do that. Every person that you think would know would just say, I don't know what this is. Well, this is the case where the combinatorics is pointing to some sort of commutative algebra or algebraic geometry I'd like to have. Now, if you don't like algebraic geometry, you can write in terms of Boolean algebras. This gives a decomposition of these partitions into sums with Boolean algebras here, q plus 1s to powers. So you can think in terms of cosets. What is this decomposition of this coset? I don't know what that is. So this leads to interesting questions of trying to understand why it's true. Okay, now I'm going to talk about the QT binomial coefficients. Well, this is going to be, in some sense, the Q analog of the Q analog. So we already saw that Q originally had two different formulations. It could be a prime power or it could be a generating function parameter. I want to decouple those two different Q's and have one of them to be a Q and one of them to be a T. So here's the definition of this QT binomial as a quotient of polynomials in T. It is not a polynomial in Q. It is not symmetrical in Q and T. And for this definition, we need Q to be the integer. Although there are ways of getting around that, but let's just assume for today that Q is an integer. Let's see what facts about this QT binomial are already known to exist. Fact number 1. If Q is a positive integer, this thing is not a rational function. It is a polynomial and has positive integer coefficients. Great. Let's skip fact number 2 for the time being and look down at fact number 3. You can take two independent limits of this QT thing and get the Q binomial. Namely, either let T go to 1 or let Q go to 1 by rescaling T. So there's two independent limits retrieving the Q binomial. Fact number 4 says this thing, unfortunately, is not symmetrical. N choose K is not N choose N line 3. There's a good reason for that. Namely, fact number 2, that these coefficients that are positive, which are given in fact number 1, actually form a Hilbert series of a certain ring of invariants. The Hilbert series of the invariants of a maximal parabolic subgroup fixing a k-space modulo the invariants of the whole general linear group. So that's what these coefficients to number 1 count in terms of invariant theory. Well, is there a formula like n choose k is a sum over lambda q to the size of lambda? Yes, here's such a formula. N choose qt is a sum over all the lambdas. A certain horrible power t that I'm not going to really write in exactly what it is, but I could. Timed a nice little quotient. So for example, if t were equal to 1, this quotient would just change into q to the lambda I. The product of q to the lambda I is q to the size of lambda. It's exactly the formula we had before. So you can think of this as kind of like an inversion or inversion for this qt. Right now I don't know a MAJ version because we don't have the right basis for this covariant algebra around. We like a MAJ kind of a basis. We don't know what that is. So you might also want to know about the Z version. If you were to do this in multisets, you can define this all in multisets. I don't know what that is either. So it's a good thing to figure out. You might think of it like this also. Since when t equals 1, this counts the number of subspaces, is there some t statistic on subspaces for which this is the generating function? And the answer is yes. I can write down some complicated statistics so that it is the generating function of those subspaces instead of subsets, or instead of partitions. So the usual things you would like to have true are true. They're working beautifully. Okay, let's try putting q equal to be a negative integer now in this. So q is a negative integer. Let's go back to the formula there. Q is a negative integer. Well, these powers of t might be negative powers of t maybe. That's okay. We're still going to have some kind of rational function of t. It's not a problem. And it has the property that if t equals 1, we do get our original n choose k prime thing. It's a t version of that. It's exactly what we hoped for. Well, not only is it exactly what we hoped for, but that is a Laurent polynomial. It's not a rational function. It's an honest-to-goodness Laurent polynomial. And all the coefficients are positive. All coefficients are positive. They don't alternate plus minus, etc. It's looking like a Hilbert series. It's trying to be a Hilbert series for us.
But there is no way you can multiply the polynomial by power of t to make it a real polynomial?
We could multiply by power of t, make this a polynomial, yes. And you can figure out exactly what that power is.
You can figure out.
Yeah, it's not a hard thing, but it just adds more complication. So I'm not going to do it during this talk. So this is kind of looking like it should be related to some invariant theory of f sub minus q. As if there's some kind of a negative, a field with a negative number of elements. And it should come from some sort of reciprocity theorem, changing q to minus q. I don't know what those are. Let's move on to the sure function. The sure function is a submetric function in some number of variables. It depends upon a partition lambda. And it has the property that if lambda is a single row or a single column, then this principally specialized sure function is a q-binomial. So this is going to generalize what I just talked about, the sure function. It also has a nice property that if you take lambda to be a rectangle, this sure function gives the McMahon box theorem for plane partitions inside a box. Well, it turns out that there's a sort of the q analog of the q analog of this sure function. I'm calling here s of capital lambda. I'll show you what it is on the next slide. But right now we just have to know it's a polynomial in t with non-negative coefficients, and q is a positive integer. Same properties that we had before. So this says there's some kind of q analog of Klopstock tableau and of the McMahon box theorem. What is the q analog? Instead of putting numbers into the boxes, you start putting in these q numbers into the boxes. And then there are certain inequalities and special ways that these q numbers show up in the boxes. I'm not going to describe it. Too late in the day for us to contemplate such a horrible definition. Like here's the definition of this funny q analog of the q analog. Again, it's a quotient of determinants. Now the determinant is, instead of raising an x to a power, we raise x to the q to a power. If you take this definition, it is not true that it's a polynomial in the x's. It will still be a rational function in the x's. So you don't get sure polynomiality from this definition. But it is true that when you specialize those x's to be 1t up to t to the n, it is a polynomial in t. There's no rationality involved. It will turn out to be a polynomial in t. And it does have positive coefficients. So the final thing of my talk is, what happens if q is a negative integer? Q is a negative integer, then it seems to be true that multiplying by a certain negative sign, you do get a Laurent polynomial in t with non-negative coefficients again. Might indicate there is something like a field with a negative number of elements. That's it.